Here are some key parameters when looking at this. So glass transition temperatures, melt viscosities, plasticizers, and you can very clearly see that as you improve the physical stability of the system, you tend to decrease the chemical stability of the system. So it's a very important interplay to try and make this into an ultimately processable but a stable formulation over time.
And in your presentation, you showed a slide about the impact of key matrix polymer properties, where when you increase the physical stability of the formulation, you tend to decrease the chemical stability.
Correct.
So could you explain more about that and how we strike a good balance?
Yeah, there tends to be a little bit of an interplay, right? So in one sense, you can make a solid amorphous dispersion using a very, very rigid polymer matrix. So you scatter the drug throughout the polymer matrix using mechanical energy, and then you freeze it in place. So a very strong, rigid matrix will allow the drug to basically just sit there and not move. But this is a little bit dangerous because you're gambling that over the course of time, either temperature or humidity effects won't allow this polymer matrix to become a bit more mobile. When this happens, the drug will very slowly start to come together, and then again you go to an amorphous phase, a clustered phase, and then a crystalline phase. So in this case, by using more chemical stability, using more surfactants and more solubilizers, and using polymers that have a stronger affinity for the drug, you have a more traditional solubilization system where you're solubilizing it in the matrix rather than just freezing it in place. So both are important. You can't have it so that it's almost a semi-solid at room temperature, but in the end, you don't want to just rely on a kinetic stability of freezing everything in place.